Okay, chapter 1.6, the design of experiments. Okay, so in this section we're going to further develop the idea of collecting data through an experiment. An experiment is a controlled study conducted to determine the effect of varying one or more explanatory variables or factors, right? Has on a response variable. So varying one or more factors on a response variable. Any combination of the values of the factors is called the treatment. Okay? The experimental unit or subject is a person, object, or some other well-defined item upon which a treatment is applied. We often refer to the experimental unit as a subject when it refers to a person. Okay? The goal in an experiment is to determine the effect that various treatments have on the response variable. A control group serves as a baseline treatment that can be used to compare to other treatments. And a placebo is an innocuous medication, such as a sugar tablet, that looks and tastes and smells like the experimental medication. In an experiment, it's important that each group be treated the same way. It's also important that individuals do not adjust their behavior because of the treatment that they're receiving. Okay, so many experiments use a technique called blinding. Blinding refers to non-disclosure of the treatment an experimental unit is receiving. So you don't tell the person what they're receiving. Okay, there's two types of blinding, single blinding and double blinding. A single blind experiment is one in which the experimental unit or subject, right, does not know which treatment he or she is receiving. A double blind experiment is one in which neither the experimental unit nor the researcher in contact with the subject knows which treatment the experimental unit, the subject, is receiving. All right, so let's look at an example. The English department of a community college is considering adopting an online version of the freshman English course. To compare the new online course to the traditional course, an English department faculty member randomly splits a section of her course. Half of the students receive the traditional course, and the other half is given an online version. At the end of the semester, both groups will be given a test to determine which performed better. All right, so who are the experimental units? The students in her class, right? Students in her class. What's the population for which the study applied? It's still the students in her class. She took all the students in one of her classes, right? So that's the population too. What are the treatments? Okay, well, she's got traditional versus online. So traditional versus online. What is the response variable? Okay, at the end of the semester, they're going to be given a test to determine which performed better. So their test score. Why can't this experiment be conducted with blinding? Well, that should be obvious. The teacher and the student will know if they're doing the traditional in-class course or an online course, right? You can't prevent them from knowing which section they're in. Okay, here's the steps in conducting an experiment. So step one, identify the problem to be solved. This should be explicit. It should provide the experimenter direction. It should identify the response variable and the population to be studied, okay? And that's often referred to as the claim. So identify the claim. Step 2, determine the factors that affect the response variable. Once the factors are identified, it must be determined which factors are to be fixed at some predetermined level, that would be the control, and which factors will be manipulated, and which factors will be uncontrolled. Step 3, determine the number of experimental units. So as a general rule, choose as many experimental units as time and money allow. Techniques exist for determining sample size, and we'll talk about that later. Step 4, determine the level of the predictor variables. So control first. There's 2 ways to control the factors. Set the level of a factor at one value throughout the experiment. If you're not interested in its effect on the response variable, okay? Set the level of a factor at various levels if you are interested in its effect on the response variable. The combinations of the levels of all varied factors constitute the treatments in the experiment. Now, step 4, part 2, randomize. Randomize the experimental units to various treatment groups so that the effects of variables whose level cannot be controlled is minimized. The idea is that randomization averages out the effect of uncontrolled predictor variables. Step 5, conduct the experiment. So one thing is replication. It occurs when each treatment is applied to more than one experimental unit. This helps to assure that the effect of a treatment is not due to some characteristic of a single experimental unit. It's recommended that each treatment group have the same number of experimental units. 5B, collect and process the data by measuring the value of the response variable for each replication. Any difference in the value of the response variable is a result of differences in the level of treatment. So step 6, test the claim. This is the subject of inferential statistics. So inferential statistics is a process in which generalizations about a population are made on the basis of results obtained from a sample. Provide a statement regarding the level of confidence in the generalization. Methods of inferential statistics are presented later in the text. Okay? A lot of this is going to be presented later in the text. We're just getting an idea right now. Generalities, right? General idea. So let's look at an example. A completely randomized design is one in which each experimental unit is randomly assigned to a treatment. So here's an example. The octane of fuel is a measure of its resistance to detonation, with a higher number indicating higher resistance. An engineer wants to know whether the level of octane in gasoline affects the gas mileage of an automobile. So assist the engineer in designing an experiment. Okay, that's all we're going to be talking about right now. So step 1. Remember, step 1 was identify the problem to be solved. So the response variable is miles per gallon. So they really should have also stipulated the population in step 1, right? You identify your response variable and your population. Okay, so our population here, we'd have to see what kind of automobiles they're testing. Step 2. Step 2 is determine the factors that affect the response variable. Okay, so they've listed factors that affect miles per gallon. Engine size, outside temperature, driving style, driving conditions, characteristics of cars. Step 3 says determine the number of experimental units, and they just say they're going to use 12 cars, all of the same model and year. Okay? So, and remember, you use as many experimental units as time and money would allow. Apparently it allows them 12. Step 4 is determine the level of each factor. So they're listing the variabilities and their level. Octane level, right? This is the list from step 2. Manipulated at 3 levels. So they're going to have 87 octane, 89 octane, 92 octane. They're going to keep the engine sizes all the same. The temperature, they can't control the temperature, but they're going to keep it the same for all 12 cars. Okay, the driving style and conditions is going to be as fixed as possible. In other words, all 12 cars are going to be driven under the same conditions on a closed track. Okay, there'll be a little variability there just from person to person's driving differences. Other characteristics of the car. So again, they're going to try to keep it as fixed as possible, making all 12 cars the same model year. Okay, still a little variation from car to car. So to account for that, we randomly assign the cars to the octane level, right? And unless they're having the same driver, they need to also do that up here. Okay, step 5 is to actually conduct the experiment. So randomly assign 4 cars with 87 octane, 4 cars to 89 octane, 4 cars to 92 octane. Give each car 3 gallons of gas, drive the cars until they run out of gas, compute the miles per gallon. And step 6, test the claim. Determine whether any differences existed in miles per gallon. Okay, so you kind of get the idea of what to list under each step when needed. Okay, here's kind of a flow chart of what happened. Random assignment of 12 cars, split it up into groups of 4. Okay, another type of experimental design is called matched pair design. A matched pairs design is an experimental design in which the experimental units are paired up. The pairs are matched up so that they are somehow related. That is, the same person before and after a treatment. Twins, husband and wife, same geographical location, etc. There are only 2 levels of treatment in a matched pairs design. Okay, in matched pairs design, one matched individual will receive one treatment and the other receives a different treatment. Okay, it's just a pair. The matched pair is randomly assigned to the treatment using a coin flip or a random number generator. Since it's just always 2, you can flip a coin. Then look at the difference in the result of each matched pair. So let's look at an example of that. Okay, excuse me. Xylitol has proven effective in preventing dental caries or cavities when included in food or gum. A total of 75 Peruvian children were given milk with and without xylitol and were asked to evaluate the taste of each. So the researchers measured the children's ratings of the 2 types of milk. What is the response variable in this experiment? Okay, notice they said rating. The children's ratings of the 2 types of milk would be better than just saying rating. Okay, be clear with your answers. Think of some of the factors in the study. Which are controlled? Which factor is manipulated? Okay, so the age and gender of the children is controlled, right? They chose 75. Also, nationality, right? Age, gender, nationality of the children is controlled. And the factors that they're manipulating is given on milk with and without xylitol. What are the treatments? How many treatments are there? Milk with xylitol and milk without xylitol. 2 right? There's always two in a matched pair design. What type of experiment is this? It's a matched pair design. Identify the experimental units, the subjects, right? The 75 Peruvian children. Why would it be a good idea to randomly assign whether the child drinks the milk with xylitol first or second? And that's to remove any effect due to ordering that we talked about earlier in our bias, right? Ordering in which the milk is drunk. Think about this. You know, one's drinking milk with xylitol, one's drinking it without. So it could influence the second person's, knowing what the first person's response was. Okay, so if they swap that around, it would help remove that effect. Do you think it would be a good idea to double blind this experiment? Definitely. Definitely, definitely. The children and the researcher giving the children the milk shouldn't know which one is getting. Okay. This ends up chapter 1 with all of our definitions and a lot of wordiness. So let me know if you need anything, and I'll see you again for chapter 2.